Okie dokie. In red, it says the strength of an electric field is defined as the electrostatic force per unit charge on a positive test charge placed in the field. So gravitational field strength was the gravitational force per unit mass. The electric field strength is the electric force per unit charge. So again, there's this mathematical pattern recurring. The field strength is the force divided by the quantity that causes the field. For gravity, it was mass. For electric fields, it's charge. And it's defined as the force that would affect a positive test charge, just as we had for the electric field arrows. A test charge is a charge, yep, as we said before, it's small enough that it doesn't noticeably affect the fields. E, our electric field strength, like G, our gravitational field strength. They're both vectors because they are equal to vector forces per unit scalar, if you get what I mean. We have forces, which are vectors, and we're just dividing them by scalar quantities. So the resulting quantity is itself a vector, and it acts in the same direction as the electrostatic force F. We don't see any minus signs or anything like that. A negative charge causes E to point in the opposite direction. Okay, so the only case where the electric field will point in the opposite direction is if this quantity Q is negative. It will reverse the direction of the field. So the definition to remember from this page is E equals F over Q. Very important. And if we have E equals F over minus E, for example, an electron, then we'll end up with a vector that is pointing in the opposite direction to F. Sorry, that is supposed to be F with a vector line underneath rather than a sort of weird jointy E. A charged particle in a uniform electric field. Okay, so uniform electric field, it'll have a uniform force on it, and it'll therefore have a constant acceleration. So it'll deviate from its path. It will. It'll form a parabola, just as if it's falling in a gravitational field on the surface of planet Earth. We said the gravitational field on planet Earth near the surface is a uniform field. And we also know from our projectiles work yesterday that projectiles travel in a parabola. But it's the same story here. We've got a particle moving in a uniform field, and it's going to move in a parabola again. That's because it, like on the surface of Earth, where they are experiencing a uniform acceleration in a direction due to gravity. Here, again, our particle is experiencing a uniform acceleration, except this time it's not due to gravity, it's due to electrostatic forces. The force is the electric field times the charge of this particle. So let's say it's a proton. It's got charge E. But we also know that F is equal to ma. So what's acceleration equal to? It is equal to the force divided by m, which is in itself equal to E times the electric field strength divided by m. Once we've determined the constant acceleration, we can apply the Suvat equations. Yeah, we've got constant acceleration, so there's no reason to not use Suvat. We can neglect the effect of gravity because, as I said before, compared to the other three fundamental forces, gravity is just very, very weak compared to electrostatics and the nuclear forces. Okay. This question looks like it's based on Millikan's oil droplet experiment. A spherical, nice oil droplet of radius 0.5 millimeters, watch out for the millimeters, has an electrostatic charge. It's suspended between two oppositely charged plates, which implies it's going to be a uniform field. In a field with electric field strength 5.2 times 10 to the minus 6 volts per meter, directed up such that the force that the drop experiences an electrostatic force that balances its weight. Calculate the charge of the oil droplet. The density of oil is given as 870 kilograms per meter cubed. Okay, calculate is our command word. 3 marks. We're expecting 3 steps in our calculation. Okay, so this is the picture formed by the question. And we have the droplet has mass, so it has weight. But balancing it out, it has an electrostatic force. We can deduce then that this is a positively charged droplet. It's being repelled away from the bottom surface and attracted to the top. And the only thing that is preventing it from rushing up to the negative plate is its gravity. Okie dokie, we are trying to work out the charge on this oil droplet. We've got equilibrium between two forces, so we want an expression for the force due to the electric field, F equals EQ. And we also want the mass of the droplet, mg. But we're not given the mass. We're not given, and so setting these equal to each other, that's the basis of our equation. We're not given the mass, we'd like to work it out. What we are given is the density, and we're told it's a sphere. So its volume is 4/3 pi r cubed. Yep, mass is density times volume. Multiply those two together. You're given all the information you need to calculate it, and you end up with this as your mass. What else did we need? We want the charge. We are ultimately after this little fella. We are told the electric field strength, I believe. Yep. So we know this, we know this, we now know this. Okay, we're in a perfect position. Determine the charge of the droplet, mg over E, sub it all in. 0.859 coulombs. Yep, something on the order of coulombs is totally reasonable. If it was 2